Ayesaac is a conversational agent for those with visual impairments. This project was sparked from a shared desire to create a tool or something to help those who were blind and partially sighted. When researching current solutions available to this user group, we saw that there are multiple solutions from widely available general-purpose assistants such as Siri and Alexa, to more focused solutions in the form of software like TapTapC or hardware like the Orcam MyEye2. However, all proposed solutions appear to operate independently from other services, which leads to reduced user choice, being restricted to limitations of the given system, and the inherent requirement to juggle multiple systems. With this in mind, we propose an end-to-end modular natural language processing pipeline to aid in the creation of conversational agents for those visually impaired. We understand that technology continues to evolve rapidly, with new research and innovations released constantly. As a result, we felt that an open-source, modular, easy-to-use framework which developers could use as a foundation to integrate their own solutions was the most useful way to contribute to this research area. Additionally, when reviewing literature to determine our experiment domain, we found that people who are visually impaired say they have the greatest difficulty with meal preparation. Therefore, we pivoted our problem domain from the living room to the kitchen.
For this project, we used Python 3. The two main reasons why we use Python are because it contains many useful libraries like TensorFlow, Rasa, Keras, OpenCV, etc. And also because Python makes the manipulation of data structure very user-friendly. We've opted for a microservice-oriented architecture for 5 main reasons. Firstly, it is easier to work as a team on microservices since the code is nicely separated. Secondly, it forces to blend upfront the major pieces of the software. Thirdly, it makes the code cleaner since each service only does what they are supposed to do. It is easier to maintain and implement features. Finally, it makes the whole pipeline run concurrently since one service corresponds to one process, which gives a boost in speed. Each service uses a RabbitMQ, an open source message broker, to communicate with each other. To improve interaction with the framework, we ensure it has a minimalistic interface where it takes the audio, image, and text as inputs and returns a response. The end user will not need to adjust the framework. Now I'm going to give a quick explanation for each of the services used in Ayesaac from top to bottom. The automatic speech recognition transforms an audio query into a text query. It uses IBM Watson, which provides the state-of-the-art in ACR. The only downside is the limited number of free requests per day. The natural language understanding analyzes the query to determine the intent underlying the question. It uses Rasa to train an NLU model only. However, its accuracy is highly dependent on the training data. The manager determines the path for the package to follow inside the dialog manager, depending on the intent of the query. The camera manages the extraction of visual inputs from a single or multiple cameras. The object detection identifies the objects and their location within the visual scene. TensorFlow Object Detection API was implemented for the service as it provides a collection of pre-trained machine learning models that can be directly used. The optical character recognition extracts the text found in the frame. The open source Keras OCR library was used for this service, which can achieve comparative performance to services provided by AWS and Google. The color detection service determines the most common color of each object within the scene. This uses the slick segmentation algorithm to reduce the number of colors in the image before using KNN to determine the name of the color with the greatest frequency. The spatial detection determines the absolute horizontal position of each object relative to the frame. The interpreter service waits for all the response and merge all the data before sending it to the NLG service. The natural language generation produces a text response given the intent of the NLU and the information gathered in the service related to vision. It uses a rule-based approach with predefined templates to return a natural language response. The text-to-speech converts generated text to an auditory response using Google Translate TTS API.
We ensured that the system could be given a request and send out a response. However, to test how this would work in a production environment, we decided to containerize and deploy the framework on a DigitalOcean droplet. We created a simple website as an example front-end interface which takes an image from the user along with either voice or text input and returns a response. We opted for the containerized approach for the microservices by orchestrating them with Docker, as it meant our development and production environments were the exact same, as the virtual environments used for development could be deployed without issues, reinstalling dependencies, or any other issues that can arise. Loading up the test image of some objects within the kitchen, we can ask it questions such as, is this a bowl, and receive a response. Through deployment, we were able to secure requests by using cores to only allow requests from our specific domain. Including this option within the framework allows future developers to easily follow best practice and secure their application. Additionally, for the purposes of this demo, we didn't store any information regarding the queries.
We ran our performance evaluation on a laptop that didn't have too much by way of resources. We saw the benefits of the architecture allowing the services to run concurrently when we reduced the runtime from 21 seconds with a linear path to 12.4 seconds when running steps in parallel. We reckon this difference in performance is defined by the parallelization of only the image processing sections of the pipeline in the dialog manager. The various language sections are all required in sequence. However, the language aspects of the pipeline wouldn't benefit all that much from running in parallel anyway, as they are currently using pre-trained models or rule-based decision-making that are pretty lightweight. We were pleasantly surprised by the performance of the system when deployed on DigitalOcean as a droplet, as we received responses from the system within about 5 seconds. We ran our evaluation on a laptop, and from that we realized that the hardware requirements for running this are not particularly large. The droplet likely performed better than the laptop because the laptop would have been running multiple background processes, whereas the droplet was only running Ayesaac through Docker. You might be able to see that the amount of resources they have is fairly comparable. Interestingly, given the current specs of modern smartphones, it might be possible to deploy this directly within an app instead of interfacing with a web server. For example, the Snapdragon 855 processor in the new Google Pixel 4 has more gigahertz of processing than our test laptop, and also has a mobile GPU that might be usable for integrating deep learning model inference, and also one of those Google Tensor processing units that maybe we'd be able to use as well. We use a couple of API services for text-to-speech and automatic speech recognition, and if we could change these to offline ones, for example replacing the use of IBM Watson with something more contained, then one solution could work entirely offline within one phone app, which would be very valuable to our users.
When testing the system as a whole, we found that 77% of the time intents were correctly identified, but only 39% of the questions were answered correctly. This graph shows that the majority of incorrect answers were due to misidentification of objects by the object detection. However, we also found that our system was unable to handle synonyms such as mug and cup, something we hadn't realized would of course be a problem. We plan to test with real potential users as well, but unfortunately we've not been able to do so due to the current pandemic.
Before any particularly lofty goals of further work are undertaken, we reckon the current framework would need a bit of refactoring to further separate the microservices, to remove any side effects that come as a result of running any one service. Doing so will provide a stronger foundation for additional features, as they'd be easier to maintain and extend, and therefore increase the chance that this framework is adopted more widely. All software projects have to strike a balance between building the desired features and maintaining code quality, and this would be a good point to rectify that balance in this project. While we're there, the current system has had no profiling and optimization performed at all, and undertaking in this task would be an easy improvement to make the system more usable. Another area we could improve would be in the training datasets used for our deep learning models. The Microsoft Cocoa dataset used in the object detection service gave us a good start for detecting common objects. However, it was trained on objects that we don't really need in the kitchen domain and could be improved to include some with more unusual kitchen items, for example, cheese graters. A significant benefit for the object detection task would be to train the model using a dataset more closely related to the environment the system would be used in. Similarly, the NLU service had issues with accurately predicting the correct intent for questions asked, a problem which can be better addressed with an improved training dataset.
The pre-trained models that were used within the Vision services performed decently, but are not state-of-the-art. This was especially clear for object detection and OCR. Improving these models would directly improve the services and the overall effectiveness and precision of the system. After improving efficiency, better hardware can then be used in deployment to use more intensive but more accurate models, leading to a more reliable system. Additionally, improving the speed of the pipeline can help make the system more enjoyable, as users will not be waiting for long before getting a response. Using depth data to make spatial detection more informative was an idea we wanted to implement from the beginning, but current events meant that we didn't have access to a Connect anymore. Also, our solution currently doesn't support synonyms or similar words. In some cases, we would miss an answer just because another word is used to describe the same thing, for example, bowl versus dish. One possible way of improving this is by normalizing the semantics of phrasing using mapping within a knowledge base such as WordNet.